Sequential timings of a pendulum don't give us a very good normal curve. I suspect that the influence of one timing on the next messes up the normality of what should be, or what might be expected to be, a normal distribution. So I did non-sequential timing of the pendulum. I didn't time every cycle. I skipped at least one cycle between timing of the interval of the pendulum, between one point and the next, or timings of the period of the pendulum. Did this for an 87 centimeter pendulum whose ideal period is 1.865 seconds. The mean and standard deviation based on 32 cycles was 1.875 second period, which deviates from this by about 0.01 second. And the standard deviation of my timed intervals was about 0.05 seconds, 0.049 seconds. 6 intervals were below, to the left of one standard deviation below the mean. 6 of the intervals were more than one standard deviation on this side of the mean. 5 more than one standard deviation on this side of the mean. The other 21 were within one standard deviation. 21 over 32 is about 0.67. We expect 0.68 or 68% of our trials to be within one standard deviation, which was pretty much the case here, and the rest outside of one standard deviation. While sequential timing is not very consistent with the normal distribution, there's at least some indication based on my 32 interval trial that we do get a more normal distribution when timing the intervals independently rather than sequentially. So this, of course, is something that should be investigated much more thoroughly, but there's at least an indication, and there's actually a good basis for an independent experiment for anyone to do. Okay, now another aspect of the statistics here is if I did many 32 interval non-sequential timings, I would expect my results to still be pretty close to the ideal result or to the actual result. Now the actual result and the ideal result will differ just a little bit because there are factors in the room that are not taken account of by the ideal result. Still, I expect my means based on 32 cycles to be closer to that ideal result or the actual timing result than the standard deviation of the individual timings. That's because when I time 32 cycles, I kind of smooth out the unevenness in my individual timings. Now there's mathematical basis for that we're not going to go into because that requires a full course in statistics and probably a little higher than an introductory level statistics. But the point is that my 32 interval trials, if I do many such 32 interval trials, will have averages, will give us average interval times that are much closer to the actual than the individual interval timings. And we can quantify that, and again I'm not going to derive the reasons for that, by the fact that the standard deviation of those 32 trial means, if I did many of them, we would expect to be pretty close to 0.049 seconds, the standard deviation of my individual trials, divided by the square root of the number of trials, or the number of intervals timed, which is square root of 32 then, giving us a standard deviation of 0.009 seconds in the mean of 32 interval trials. Now that's one interesting and important idea. Another is that there is, I believe, mostly a neurological bias that's going to cause my mean to differ one way or the other from the actual. In other words, I'm going to have a neurological bias to time the intervals a little bit long or a little bit short. So if I did a large number of 32 interval trials, and also did a reliable timing to know what the actual time was, again, that should be pretty close to the ideal, I'd be able to determine the nature of my timing bias. Now, as I've implied, minor factors cause the actual time interval to be a little bit different from the ideal, but not that much, maybe just a thousandth or 2,000ths of a second. So, question is, based on one 32 interval sample, and that should be on one, the E should be on the second word there, on one 32 interval sample, what's the probability that my bias is for high readings? Now that would be your conclusion because this reading is high. Okay, now this isn't the actual, but the actual would probably be pretty close, much closer to this than this is. And I would still be a little bit high. Okay, by around, if we assume this is the actual, just for sake of argument, a hundredth of a second. Okay, so I'm a little bit high. And the standard deviation of my 32 trial means we would expect to be around 0.009 seconds, so that I'm about a standard deviation higher than the mean and a little more than that. So what's the probability then, if this is the only information you got about my timing, that I tend to time high? Well, you can't draw firm conclusions, but you can say, okay, we're going to assume an actual time interval of 1.865 seconds. Standard deviation for my 32 interval trials would be 0.009 seconds. And again, this 0.049 seconds is just based on one trial, one 32 interval trial. And if I did many, there'd be some variation from this, but not a huge variation. I'd say it wouldn't vary by more than 10 or 15%. Okay, so let's just assume, just best assumption we can make is that the standard deviation of my 32 interval trials would be 0.009 seconds, and I'm a little more than a standard deviation above the actual. Okay, well that seems like pretty good evidence that I'm timing a little bit high. Now I could go on with this, but I'm not going to, and anything else I would say would tend to be misleading, except to say that if I'm here on the normal distribution, I could, one time in about 5, 6, or 7, accidentally fall this much above the, or my standard deviation could cause me, not saying that well, even if I was timing with complete accuracy, it would be likely, with this much standard deviation, that one time in 6 or 7 32 interval trials I would fall that far above. So I could have just by chance fallen this far above the mean. And really, I'm really timing it very close to the actual. And on a number of 32 interval trials, I might fall here, I might fall here, here, okay, somewhere close to the mean. On the other hand, inherent bias says that if I did this many, many times, if I had many, many 32 trial timings, okay, I could fall out here. I'm going to tend to fall toward the middle more often, not too far from the middle most times. Okay, if this represents a bunch of 32 trial means, then according to this picture, I'm thinking that I probably fall about here, and that's maybe just a little more than the ideal. I'm a little bit to the right of this curve. Now that might not all make complete sense. I would have to state this in a lot more detail, which would probably be more confusing than just leaving it where it is. So I'm going to leave it where it is.